Okay, so our next speaker is Topaz Gilad. The topic of the talk will be From Cost-Sensitive Classification to Regression, Unlock the True Potential of Your Labels. Topaz is the VP of AI and Algorithms at Voyage81 to ODDITY. Topaz is an experienced R&D manager specializing in AI, machine learning, and computer vision. Currently in, as we said, Voyage81 ODDITY, formerly in Pixelot, and also an advocate for women in tech.
Thank you. Thank you for the intro. Okay, so hi again, I'm Topaz. I'm a mother of two and currently working on the deployment of the next generation right here. And I'm also the VP of AI at Voyage81 ODDITY. ODDITY is the largest direct-to-consumer online beauty and wellness company in the world. And today we will discuss about a topic that is highly relevant in applied research, and those are the inner relations between your target labels. And we can see how acknowledging those relations can really boost the information you provide during training, also just improve the robustness of your model and better model the world. So what's on our agenda? First, categorization to see the hidden assumptions that we take there and limitations. We'll continue to acknowledge the inner relations between target labels and how to take those into account in our design. And then our coarse categorization will meet the continuous real world. And finally, I will share a decision diagram that can help and guide you in your next classification problem. So starting with classification. Given the set of those images and asked to classify them, let me ask you, is a giraffe closer to be an elephant or a lion? This question obviously is relevant in the context of the information data that we have. Those target labels are independent. So the straightforward way to solve such a problem is, of course, nominal categorization, using the most common loss function for that is the cross-entropy loss. And of course, with the one-hot encoding, where only the entry of the true category is set to the value 1 and the rest are 0. But let's see what really happens when we use that simple approach. So basically, when we use the cross-entropy, only the entry of the true category contributes to the loss function, so only the confidence of the true class. And the remaining, the residual, the way the softmax divides the residual of the confidence between the other categories doesn't influence the loss at all, doesn't contribute to the training. But we know that some misclassifications have higher risk than others. If I want to predict the weather for the weekend ahead, if the true prediction should be sunny, and the second best prediction my model predicts is cloudy, not too bad. But if the second best is stormy weather, this will definitely ruin our weekend plans, right? So we need to take that into account. So let's put things into order. Because if we stop to think about it, many of the categorization tasks around us actually have inner relations between the target categories. They have an order. If it's trying to predict product ratings, how satisfied will a user be with a product match? Or age prediction, and of course, in the healthcare industry, trying to classify different severity levels of a medical condition. So let's consider, in the context of neural networks, basically ordinal classification was first introduced in the Anon Rank paper, where they suggested instead of using the one-hot encoding, use a different encoding to encode that order between the categories into your learning structure. So basically, all the entries up until the kth entry of the K class are valued 1 and the rest are zeros. What it does? Basically, our labels are no longer mutually exclusive. So we cannot use a softmax, use a sigmoid instead. And in addition, we get a distance between categories. So there is a different distance between each set of class. And still, the distance is uniformly spaced. So those are uniform steps, but we get an order. And this order matters. We can see in this example, trying to, for example, given an image, and you are asked to predict the stress level that this plant is experiencing. Is it healthy? does it have some kind of a disease? As in many categories that describe a process through time, the target categories have a relation, they are ordered. When we'll try and classify such a setting using classical categorization and do not introduce the order at all during our training, we may end up with the undesirable situation right here, where the healthy cluster, the no stress cluster in the feature space, is really adjacent to the severe cluster. And we can see that in the confusion matrix as well. The y-axis is the true class, the x are the predictions. We can see that that model, on that test set, 20% of the true severe categories actually got a prediction of no stress at all. So consider that even if your accuracy is high, the nature of the remaining mistakes should matter. Now let's see what happens when we use ordinal classification instead. When we use ordinal classification, we help the model to understand those interrelations faster, to converge faster to a more desirable situation. We can see now in the feature space that the order between the clusters makes more sense. And we can see the nature of mistakes is better, closer to the main diagonal. And of course, remember that accuracy only balances between the true predictions and the false ones, and doesn't give you any information about the nature of the mistake. And we should care about those. But still, why we chose 5 categories or 3 categories? This seems a bit arbitrary. Because, as you can see right here, in this example, I only took snapshots from time-lapse video that actually tracked that plant for 5 whole days. So the world around us is basically continuous. It's just our minds that are discrete. So we need to ask ourselves, I mean, as human annotators, when we are asked to make really fine-grained classification decisions about a continuous situation, we lose objectiveness. We become subjective. And do we want our models to mimic our own limited human annotations abilities, or do we want them to outperform us? So how do we do that? How do we take the human coarse annotations and bring those to the next level, continuous level? Sorry for that. Some categories do not have a clear cut, so it's really not clear in the presentation as well. For example, when we're trying to predict age groups, and arbitrarily, because of some kind of product need, we say that teenagers are up to age 18 and young adults 19 and above. This may be arbitrary because this 18-year-old right here doesn't distinctively belong to one category more than the other, right? She has a shared membership in both. And let's say that tomorrow you will open a new market in a new country, and there young adults are starting from age 21. What will you do? Will you retrain the model? Will you re-annotate? So we want to incorporate the shared membership into our learning. Sorry. Let's take a look at the cluster. We have marginal samples between those 2 clusters, and basically we would like to introduce the shared membership into the target labels. So instead of one-hot encoding, using the membership to each cluster as your targets. And basically, using soft labels was shown in a famous Hinton paper to not only improve calibration, but also reduce overconfidence of your network. So of course this is desirable. But still we have this arbitrary K again. And what can we do if we need to change the number of categories or just be more adaptive in production? So there is really just a nice trick around that. We can use weighted averaging, mapping between the fuzzy memberships into an actual one number. Weighted averaging between the number of the category and the soft label. This basically takes us from a discrete distribution into a continuous one, from classification to regression. Just remember, if you use that, that your target distribution was discrete. So when you interpolate, you will have those values in your target distribution. Those are not real. Those are just artifact of the way you interpolated. So you find yourself with an unbalanced regression. Take that into account. Definitely use augmentations or balanced MVC, etc. to address that. And finally, this is what we'll get. If we'll use regression on the right, we can see that previously on the left, the clusters really condensed. They had an order, but they were condensed. With regression, those are smooth, and you will not have the margin. And why is that desirable? Why should we prefer overlap instead of a margin? Because we do not want to overfit a difference between an 18-year-old and a 19-year-old. So just next time, consider relations between your categories and help guide you to make a better decision. Thank you.
A very quick question, someone? Okay.
How to create such kind of labeling? In creating classical labeling, it's very time consuming. If I now need to label more than one cluster, it's become unpractical.
I didn't hear the question. Can you repeat?
How do you create such labeling? It's very difficult to create traditional labeling. Am I?
Yeah, but now it's even more time consuming because I need to label not just one cluster. I need to label a lot of classes with some weight
So basically, you label the same way that you labeled before, but you use an additional information. It could be voting between different annotators that chose those core categories. Many people, they say, for example, the human annotation was noisy, but it wasn't noisy. The lack of objectiveness, you can leverage that into the softness and learn from that. And you can use priors from different knowledge sources as well.
Thank you very much.